So welcome to the another lecture of data structure, which is on graphs as well. So in this particular lecture, we will be covering the topic of searching something in the graph, right? So when we say searching in a graph, so what happens is that we have nodes in the graph and they are connected with each other, right? And the data which is stored in the graph is in the node, within the node, right? For example, here 2 is saved, for example 6 is saved here, or 8 is stored here, and 7 is stored here. So we need to search, if we need to search something, so we need to have mechanism. Like if this were an array, then we would have simply used one for loop and started from the index number 1, then we would have gone to index number 2, and so on and so forth. But this graph is so unstructured that we need to have a mechanism from which particular node we are going to start the searching process, and after traversing or checking or searching within one node, to which node we will be going in next to search the item. So graph searching algorithms are important from that perspective. Okay, lucky you, you're not on campus, otherwise you were supposed to take this quiz. Anyway, so graph searching, I've told it to you how it happens, like what is the problem statement. The graph searching, we have two algorithms. The first algorithm is called the breadth first search, or BFS, right? And the other algorithm is called depth first search, right? So one algorithm works in breadth-wise manner, and the other one works in the depth way, right? So what we do is that, okay, instead of reading out this, because instead of reading, if I show it to you in shape of simulation, that will be very convenient. But I just recall that I need to tell you about this this algorithm as well. So okay, then let me use some drawings. For example, this is a graph. Okay, these are nodes and they are connected with each other, right? So the algorithm will work in such a manner that initially it will assign colors to the nodes, right? For example, initially all nodes are assigned, let's say, white color. Then we select a node, for example we select this node, right? And we say that, okay, we search the value within this node. So once we have selected this node to be searched, what we will do, we will change its color, right? For example, let me change its color to green, right? Now the white color cells or nodes represent those nodes which are not touched yet, right? I can call them unexplored nodes. But the green node is a node which is partially explored. For example, I see this node and I find whatever value I am trying to search, I go to this node, I will find. If I find, okay, otherwise I will say, oh, it's green. But next what I do, I pick neighbors of this node. Now who is the neighbor of this node? This node is the neighbor of this node. Okay, let me give names to these nodes: A, B, C, D, and E. Right? So coming back to my example, now initially all A, B, C, D, E nodes were unexplored, they were all white. I picked a node, I gave that node green color, right? it means I've explored it, but I've partially explored it. I've searched the value which I was finding. Then what I do, I pick its neighbors. Okay, let me change the example, or rather extend the example a bit. Let me connect these A and D as well. Now what I do next, I pick neighbors of A which are B and D, right? So what I do, I color them green. I color this D green as well. Now once I have explored A and I have considered B and D as well, it means A has been totally explored. So it means I will give it another color. Let me use a red color for totally explored nodes, right? So white, green, and this is not white by the right. This is red, this is green, and right. So red means totally explored. Partially explored, and white filled is unexplored, right? So this is how it works. Now once I've seen B and C as well, what I will do, I'll pick one of the neighbor. Let me pick B, and I will pick its neighbor. Now since I've picked the neighbor of B, it means the B has been totally explored here as well, so I will color it with red, right? And so on and so forth. I will be dry running it shortly. So this is the mechanism of searching in graph in a depth first search manner. Now this is the pseudocode of this breadth first search manner. This is the pseudocode of BFS algorithm, where initially we initialize all the vertices. It means by initializing we assign them one color, maybe it's white. As I mentioned earlier, white represented unexplored node, so we have to initialize all the vertices. Then what we do, we have a queue like stack and queue. So this is a queue. We have a queue where we insert the starting node, right? Now then only one node is inserted, then this while loop is executed unless we have an empty queue. Now what we do is on line number 5 we dequeue. Initially there is only one item in the queue, so we dequeue that item, right? And like this will be a node, right? This will be dequeued, and this loop does what? This loop actually verifies or goes to all neighbors. For example, this is a graph, right? And these are, so this node has been dequeued. So let me name them as well: A, B, C, and D. Now this A has been dequeued. Now it will go to all vertices which are adjacent to A. For example, it will go to B, it will go to D. C, it won't go to C because C is not adjacent to A, right? So it will see its color. Now if its color is white, it means B and D are unexplored. Then it will do what? It will give it green color, right? Sorry, gray color. Previously, a short while ago, I used different colors. They were red, green, and white. But here the colors are different. But the purpose of these colors is to differentiate between totally explored nodes, partially explored nodes, and unexplored nodes, right? So here this node and this node will be colored gray, and the distance information, like here this is distance information will be 0, here it will be 1, incremented from the parent, and a pointer will point to these nodes, right? And then these two nodes, this one and this one, will be enqueued into the queue, and similarly this process will continue. Once once all the vertices, neighboring vertices of the node are explored, this color of this node will be turned into black, right? So and this dequeue operation has its own cost. Now let me dry run this concept. Now if we see here, here we have a graph with 8 nodes. They are labeled as R, S, T, U, V, W, X, Y, right? And we have a queue. Here I'll be showing a queue. So here in the queue we put the starting node. We can pick any node as starting node. By chance we have picked this one, so that is fine. So initially all the nodes will have weight infinity, right? The starting node will have weight 0. So this is put into the queue. Now what will next happen is here that we will pick neighbors of S. R is the neighbor of S and W is the neighbor of S. So we will dequeue this S from this queue, and we will put R and we will put W in the queue. And this order can be WR as well. So that's not a big deal, but the neighbors of S will be picked, right? And what will happen, that this S, this one will become black, and these one will become green, right? Now if you see, this S has become black because it has been completely explored. R and W have been put into the queue, and they are now green because they are in ready state, and the rest of the nodes, they are white because they are unexplored, totally unexplored. Now the node which is in the front of the queue, this will be explored. Now its neighbors, like this T and this X, this T and this X will come into the queue, and this W will be removed from the queue. Now if you see here, now T R remained there, T and X were enqueued in the queue. Now one thing you notice, that here the distance was 0, now here this distance is 1, now here in the next step here the distance will be 2, right? Now look at the queue, look at the queue here. Now it's the turn of R. Now what will happen, this R will be removed from the queue, and this V will be put in the queue. Now this R will become black and this one will become green. Now if you see, V has been put into the queue, right? Next we have T in front of the queue. Now what will happen, this one will become black, and its neighbor which is in ready state, like this is neighbor, this will enter into the queue. This X is also its neighbor, but since it is already in the queue, so it won't make any difference. Now the next entry of the queue will be like X, V and U. If you see here, X, V and U, right? Now okay, now if you see X, where is X? Now this one. Now what will happen, its neighbor Y will be put into the queue, and this will become black. I'm sorry, the black color is not available in this software which I'm using, so so I've written black in red color. So if you see, notice here, this will turn black, and distance will be incremented by 1, this will become 3. Now which node is in front of the queue? V. Now V is in the queue, and there is no unexplored neighbor of the V, so it will simply become black, and V will be removed from the queue. See, and again U is in front of the queue, and there is no unexplored neighbor of U, so it will become black and it will be removed from the queue, and same goes for Y. Right? So this is how we have searched the graph in a breadth first search manner, right? So this is the now these numbers basically signifies the distance of this node from the starting node. If you see here, 1 and 2, right? Here if you see this is the starting node, and this 3 here. Here we come from this node u to t, then from t to w, and from w to s. So it's the distance of this node from the starting node. The numbers and orders will be different if we start our search from, let's say, this node. That will be different. So this is how breadth first search algorithm works. And the next one is the depth first search. Depth first search and breadth first search algorithms are ditto same, with an exception that instead of using a queue here, what will you use? You will use a stack. The rest of the algorithm will remain the same. So it will, instead of working in a breadth first search manner, it will be working in the depth first search manner. Okay, let me show it to you using a tree based representation. For example, this is a tree. Tree is also a graph. Oh, बहुत बुरा बन गया. This is a tree. Tree is also a graph, but in tree there are no cycles, right? So we can also call tree an acyclic graph. So if BFS, BFS. Right? Now in breadth first search, what will happen? First of all the nodes in this layer will be, or in this level will be explored, then all the nodes in this level will be explored, and all the nodes in this level will be explored. This is how BFS works. But in DFS, how it works? It works like this. It picks the node from the top and it goes to the depth. It explores it like this. Then it explores, it goes here, and then it searches the graph like this. So this is the primary difference between BFS and DFS. Both of them have the same time and space complexity. So whichever you like, you can use, right? And one thing which I just talked about, let me explain to you. For example, this is a graph. Now if we see here, this is basically a tree because there is no cycle. But when I make a cycle, so it no more remains a tree, it becomes a graph. So tree is a subset of a graph, right? But it's acyclic. It does not contain any cycles, right? So this BFS algorithm, I have explained it to you. It's dry run. I have executed it for you. This depth first search algorithm, I told you, instead of using a queue, you simply use a stack here, and instead of using DQ, you will be using pop, right? And instead of using in queue, you will be using push. Rest of the algorithm is the same. However, I found a different implementation which works the same way. So I have pasted in the slides as well. So this is basically this algorithm and this algorithm are sort of same, but this is in a different nomenclature. So you can do that as well. Sort of this one is easy one to understand. But I hope the concept of BFS and breadth first search and depth first search is clear to you guys, right? Thank you.